Lesson 12. The title for this lesson is Contact Forces. And but before we actually proceed with this lesson, something that I forgot to do in the last lesson that I should have done is that so we have resolved a diagonal force. It's called that force F, and we resolved it into its F into X and Y component. And that X component, we said, is F sine of, I'm lying, it's F sine of cos of theta. So this force makes an angle of about theta with the horizontal. So it's F cos of theta. This one would be F sine of theta. So this was an object, this was the force that is acting on in a diagonal direction. So what about forces that are for forces that are act on an object on a slope, as we are most familiar with in class? I'm sure you might have been introduced to something like this, where maybe the slope makes that angle with the horizontal, and maybe you have an object there sitting on that slope like that. So I'm not going to draw all the forces that act on this object, only I'm going to only consider weight for now. So there we are. So we're still going to do a lesson on how to draw force diagram as well as free body diagrams. So normally, so in terms of these forces, for example, let's take weight. So weight must come from the center and it's acting downward. So let's call weight Fg. So this is the most common type of force that is resolved into what we call parallel and perpendicular vector. Oh, that is the right spelling. Doesn't matter. And perpendicular component, right? So the perpendicular component of this vector would be something like this, and we would call it Fg perpendicular. So we use this to represent that is the perpendicular component, but also it will be resolved into the parallel, so parallel to the motion of this. Maybe let's say this object was moving up or down, and then we would call this remove this, we will call this F parallel. So this is the parallel component of weight and the perpendicular component of weight. And this angle over here is the same as this angle that the slope makes with the horizontal. So now we know how is it that we found these components. An exercise that I would give you is that try to find out how did they get to say, okay, that parallel component of the weight is actually going to be given by Fg sine of theta, and the perpendicular component they say will be given by Fg parallel perpendicular, which is Fg cos of theta. So these two are very, very important, and we're going to work with them. We work with them when you're solving equations, so you will see how we actually put them into action. But now let us actually get to today's lesson. Okay, so for today's lesson, as I mentioned, we're talking about contact forces. So at least by the end of this lesson, you should be able to define the following terms. The first thing is, what are contact and non-contact forces? What is the normal force? What is tension? What are frictional forces? As well as kinetic and static frictional forces. So at least by the end, you should have a working definition of these terms, because they are normally asked in the examination. So let us just start by first defining what do we mean when we talk about a force. So a force can be defined as a sort of a push or pull action exerted on an object. So let's say you have an object, you may decide to push it. This is you trying to push, those are your hands, or maybe you're trying to pull it. So we can say maybe you're trying to push that object to move in a certain direction, or you trying to pull it to a certain direction. Just imagine that those pull or push doors, and so you're exerting a certain type of force. So like I mentioned, a push or pull action exerted on an object by another object. So you are an object and you're exerting this push or pull action on an object, and this action, it can happen when objects are two objects are in contact, or when they are not in contact. So if the two objects are in contact, we say you applying something that is called a contact force. And if the two objects are not in contact, we saying that you are applying something that is called non-contact forces. But now let us differentiate between non-contact forces and contact forces. So now, non-contact forces are exerted between objects that are a certain distance. So the space between these two forces. So imagine maybe this is like a charge is positive and negative charges. They will exert forces on each other, like the electrostatic forces. So they don't need to be in contact to exert these forces. And types of contact non-contact forces are electrostatic force, gravitational force, as well as magnetic force. And then contact forces, the two objects in question should touch, and this one will exert a force on this one, and this one will also exert a force on the other one. So examples of examples of contact forces may include applied force, tension, friction, and normal force, which are the forces that we're going to talk about today. Okay, so let our discussion start with normal force. So the definition that you should know is that normal force is the perpendicular force exerted by a surface on an object that is in contact with it. So if we have a block resting on a table, this surface of the table will exert what we call a normal force, and normally the symbol for that is Fn. So if, for example, this object is not in contact with anything, with the horizontal surface, then there would not be a normal force. So you should be able to know this definition. So let make an example that we took. Let's say we have that object is resting there, and then there is your object. We represent that object with a block. So the surface will exert a perpendicular, so it makes that 90-degree angle with the surface. That's why we say it's perpendicular with the object, and we call this Fn, or normal force. And then we know that this object will also be under the influence of weight or gravity, and then there we are. So we always draw that thing from the center, so we call this Fg. In this case, if there are no other forces, let's say for example this is a very smooth object, and there's no applied force, there's no push or pull, there's no friction, and the only forces acting on this object are just the normal as well as weight or gravity, then we can say that Fn will be equal to Fg. So this condition is only true if there are no other forces acting on this object. This normal force will change depending on the direction and magnitude of the applied force. So we'll see what I mean just now. So let us now consider a situation whereby we had an applied force to this object. So let us now say we had this block, and what then happened is that there was another force. There was a force, an applied force applied to this object. So it's no longer only two forces that are have an effect on this object. And remember, now this force actually acts diagonally to this object of ours. And so we know that we can resolve this into its x and y component. So we can say FAX will be equals to FA cos of theta, and FAY in the vertical direction will be given by FA sine of theta. But now we are only for this instance, we still only want concerned with the vertical motion. So let us define direction. Let us say up is positive and down is what you call this is negative. So now using Newton's second law of motion, or maybe even, so we'll say F net. So remember F net equals to MA. So there we are. So we want to have the effects, we're talking in the vertical direction. So remember, this object is not moving up or down at all. So it's not accelerating in the y direction. Let me just write this y so that you know it's in the y direction. So we're not really concerned for now with the x direction. So if it's not accelerating in the y direction, it means a is actually 0. So this would actually be m multiplied by 0, which is nothing but 0. So any number multiplied by 0 will give us 0. So now we have to find all the forces that are acting here on the y direction. So we know that we have gravity from the center. It's not really from the center, but yeah, from the center of this object, and it's facing down. So we call that Fg. And additionally, we will have that force of that, what is it, normal force. And also remember, because we can resolve this into its y and x component, we'll also have that x component. You don't have to draw it, but just keep in mind we have this y component also acting upwards in this case. So let me just draw it here. This, so we have FA. So remember, we can resolve it into its x and y component. So we have FAX and FA y. So we have that FAY, which is also acting upwards. So we said up is positive. So we'll actually have our normal force. So F net is just the total effect of that. Fn plus FAY, so that component, as well as Fg. But now remember, Fg, we said that it is facing downwards, and downwards is negative. So it can actually be minus Fg. Fn, and we know that we have defined Fay as Fa sine of theta, which is equals to, we can take this to the other side, which is equals to Fg, and we have that over there. So it's almost like the magnitude of the Fn changed because of the presence of this external force. So that is what you get. But now let us consider a different situation where we have the same object, but now this force is now facing this way, and it's making that angle with theta. So we still have our Fg from the center, and then we'll have Fn over here. We can call it Fa as well. We still have to resolve this vector into its x and y component, and to do that, it will be the x component. So you see it's facing to the left, which is Fax if this vector is Fa, and the y component, you see that it's facing down, Fay. And then we write again that we know F net is going to be equals to 0 because this object is not moving up or down, and now we are only considering the up and down motion. So we have Fn, we add all of those forces acting there, and then Fay is also acting down. No, this is not true. I'm not sure why I put a negative here. This was supposed to be plus. I apologize for that. So Fa, and then this would be plus, and then Fay is face down, so we have minus Fay, plus Fg, which is also down, we have minus Fg, which is equals to 0. And we know Fn minus Fa sine of theta minus Fg equals to 0. We can just take all the negative numbers to the other side, and you find your normal force to be Fa sine theta plus Fg. So those are just some of the important things to understand. So another situation we can consider is if we have an object there. Remember, we're still talking about normal force, and then this object is just hanging on a ceiling, perhaps with a rope. And then to draw this force diagram, we would just say, okay, there is Fg acting on this object, and then we also have tension. Let's call that Ft. So remember, the force of the rope is tension, and in this case we can see that Ft, so Ft plus Fg will all equals to ma, but our object is not moving up or down, so this entire thing is equals to 0. And remember, this Fg, I keep forgetting to write it, is negative. Why? Because we can say up is positive and down is negative. So we'll actually have plus minus Fg. And there we are. So we have Ft equals to plus, if you work it out, Ft minus Fg equals to 0. So there's no other force acting on this. It's just hanging on a ceiling or something over a rope or a cord. So another force that we can talk about is frictional forces, because we've spoken about the normal force, applied force, and a little bit about tension. So we can define a frictional force as that force that opposes motion of an object which is in contact with it. And then there's also something in terms of frictional forces. You were introduced to something called coefficients of friction. So remember that so these are called coefficients of friction, so mu s or mu k, and this basically, they describe the roughness of a surface. So the rougher the surface of your object is on, they created a coefficient of friction. But we can, so since we're already talking about that, we can now also talk about static friction. So we have static friction, which is given by Fs, and then it's a frictional force on a stationary object that opposes the tendency of motion. So it's a friction if your object is stationary. And then the formula for that is that we're gonna use something called Fs max, which is the magnitude of friction when the object just starts to move. So just the second before it moves, that's when we get the maximum static friction, and we define it as Fs max, and it's given by this equation, coefficient of friction multiplied by the normal force. So if you have given the coefficient of friction and the normal force, you can be able to calculate the maximum static friction. And another thing here, we also talk about kinetic friction. So this is friction when, I'm not sure what is it that I wrote there. So you have kinetic friction. So kinetic friction is the frictional force on a moving object. So remember, static, your object is not moving. But then because we have rough surfaces, you will have that force opposing it. We call it Fs. Here, your object is moving at a certain velocity, and then it also experiences that Fk. So the formula for that you're familiar with is that Fk equals to mu k, and then multiplied by the normal force. So these are just the two equations in terms of frictional forces that I wanted to introduce you guys to. And then in the next lesson, this is when we're gonna do calculations. I know this lesson was theory intensive, but you needed an introduction to these forces before we can start working with them. I hope you enjoyed the lesson. I'm trying to see if I may have left anything out, but no. So yes, I'll see you on the next lesson.